recording. Okay. Share my screen and okay, and just get the chat in so I can see what you guys are saying and get started. Okay, so welcome guys to the Let's Talk event today. And today we're going over supervised learning, ensemble techniques to be precise. We'll be going over some of the ensemble techniques that I'll be telling you about. I'm Bharadwaj. I'm your host today. And that's my Discord over there. So if you guys do want to, message me about anything, about AI specifically, and if you have any questions, do let me know. This is my Discord, and that's Hyro. Hyro, the co-SIG lead. Wants to say something. Yeah.
Hi, I'm Jairo Carreon. That's my Discord. That's me in the snow. I do the Let's Code. So if you check our YouTube channel, last time I actually did a Kaggle workshop. So if you're interested about that, interested about data science, or like just joining a data science, machine learning, AI community, make sure to watch that video and learn more about Kaggle. Thank you.
Well, thank you so much, Hyro. Yeah, if you do want to check his previous workshops, please do go to the SIG AI channel. We have a link in the chat. It's really helpful for you guys to see your missed workshops. So yeah. So what exactly is SIG AI for the people? SIG AI Let's Talk. This is for the people who are joining us for the first time. This is basically a Let's Talk is basically a place to learn something new. It's a place where you throw away your fear of speaking out. Please do feel free to interrupt me whenever you want to. I don't want to make this a place where I keep talking all the time. Questions, I know I do have a slide of questions in the end, but that doesn't mean I restrict questions only till the end. So do just unmute your mic and start talking whenever you want, or if you have a question. So yeah, and this is a place for discussion in the end. So I do encourage you guys to start talking. Okay, let's go here. And this is the schedule for the Let's Talk and Let's Code events, the upcoming events. You guys can scan the QR code. And the reason we give you this schedule is to help you to help you guys do your homework. So before coming to a Let's Talk event, you can go over what topics you're going over, or what topics we are going over, and then you can maybe search it up or learn something and share it with us. So because I'm not perfect and I would like to learn something you learned on the internet. So that would be a great way for us to learn more. And it's totally fine if you're unfamiliar with something. And that's the reason why we're having these Let's Talk events, just so that you can learn something and just take your fear out. Yep, so let's begin. So today's schedule, we're just going to go over a recap of what we did last time. And we're gonna go over supervised machine learning, decision trees, random forests, AdaBoost, which is also known as adaptive boost, gradient boost, and XGBoost. XGBoost is extreme gradient boost. So yeah, let's start. So does anyone remember from last time what the difference between a regression and a classification problem is? Does anyone remember from last time? Regression versus classification. What?
Yeah, if I recall correctly, classification had to do with grouping, and regression was predicting a value.
That's on point, correct. Yes, thank you so much, Dylan. We went over classification and regression problems, which was exactly what Dylan was saying. And linear regression, we also went over some models like linear regression and logistic regression, support vector machines, right? So just to recap, linear regression is basically a line of fit, the best line of fit. This tries to predict and place a line which has the minimum distance between all these points over here. Oh, let me actually get my pointer out so you guys can see what I'm doing. Okay, so tries to find the best line of fit. That's linear regression, best line of fit. And we also learned that there were two types of classification techniques. One is binary classification, and the other one is multi-class classification, which you have a picture here. If you want a more detailed explanation of this, just go back to our video. It's on the YouTube channel, SIG AI, it's in the chat. And logistic regression is similar to linear regression, but here we fit a sigmoid function, which is this green S over here. So you see it's trying to, it's also best line of fit, but it's basically a sigmoid function in the end. And these red dots are false examples and blue are true. So you get the idea. And support vector machines are similar to linear regression, but it's a more accurate version of linear regression. That's how I like to think about it. So it basically has two more hyperplanes, which it like sits on these vectors, and that's how it's able to predict and find the best line of fit. So you can watch the previous video. It's really good. We have a good explanation on how support vector machines are actually working. Also, you can check the slides as well. Today, we're going over decision trees. So decision trees are really important, and the decision trees don't come under ensemble techniques. You'll learn what ensemble techniques are, but they don't come under it. But we need to know what decision trees are in order to learn ensemble techniques. So the basic idea of a decision tree is that you start at the top and you work your way down, and when you end up with a node or a leaf where you just can't go anymore, that's the end. So that's how you get the sample. So you start from here, you go down, and then you figure it out. So that's the basic idea. Okay. So let's look at the structure of a decision tree, right? So at the very top here, that's the root node. So basically like the head node in a binary tree, right? So that's the root node over here. And all these pictures I took from a video which I really liked. The link is over there. Do check it out. That's how I learned decision trees. And goes into detail, which we're going to go in today as well. So yeah, these are just screenshots that I got from the video. And here, these are called internal nodes. So internal nodes are basically like root nodes, but they're not at the top, but they have arrows pointing at them, and they're pointing to other nodes. So that's how you identify if it's an internal node. And the next one and the last one are leaf nodes. So leaf nodes are like the end of each of the branches. They have arrows pointing to them, but they don't have they don't point to any other nodes. So that's how you identify if it's a leaf node or not. And leaf nodes are usually also known as leaves, and that's where you usually find the answer to all of them. So that's like the end. That's why. So here's a simple decision tree. Okay. So let's say a person loves SIG AI, right? Well, if true, then this person is awesome, right? But if false, well, this person is slightly less than awesome. So this is like a basic decision tree. So in general, it's just a way to segregate between two different things or three different things, right? And it classifies, in this example, a person, right? Another example of a decision tree is with numeric data. But how do we do it with numeric data? So let's say if a person gets more than 95% on a hard test. If false, you know the person studied hard, right? But if true, this person definitely should know. I'm just kidding. I'm just kidding. It was completely a joke. It was completely a joke. So decision trees based on ranked data, right? So we can also have decision trees with data that is ranked. For example, here we have the level of hunger. Let's say that the level of hunger 1 is very hungry or super hungry, and level of hunger 2 would be moderately hungry, so not so much, right? But you're still hungry. So in that case, you really need food. If your level of hunger is 1 and you're super hungry, you really need food. But if it's false, your hunger level is, it might be 2, like you might be moderately hungry, and maybe you just need a snack, right? But if that's not the case as well, maybe you're not really hungry, right? So that's basically a decision tree with ranked data. Let's move on. Okay, so now let's look at this. Let's look at this with an example, and let's build a decision tree from scratch. All this looks really, really simple and fun, but going into it with a data set and trying to build a decision tree is, from the model's perspective, is where it gets a little complicated, but not so much. I think you guys can handle it. So that's why I have it in here today. So today we'll be looking at a data set. We'll be considering that data set, which has the courses taken by a student, which is math, computer science, and writing here. And we're trying to predict if the person loves SIG AI or not. Yeah, so, and this data is not real. Excuse me. So this data is not real. It's just dummy data that I just randomly put in, like you see here. No, yes. See, it's just, you can literally see that I put it there. So yeah, it's just some data for us to like get the understanding of what decision trees and how to build a decision tree, right, with some given data set. So let's go. So first, our goal to build a decision tree is to find our root node. So how do we know what a root node is? I can put a root node as writing, and then maybe have a branch node as CS and then math, or I can also do math as a root node. Like, how do you know what exactly the root node should be, right? So we go through this process, right? So to find the root node, we'll first consider column-wise, and we'll take each column at a time, and we'll try to correlate if that column is we'll try to correlate the result of that column to the actual result. So because we do have labels, and this is supervised learning. So for example, now we're going to take the math column, right? We're going to take the math column and see how it alone predicts if a person loves SIG AI or not. So let's take the first example, right? Let's find the root node for this entry. Sorry, not the root node. We'll count how many. We'll count the correlation between the yes and the no for the math column and the SIG AI, if a person loves SIG AI or not. So for math, yes. So here, this entry, the person has taken a has taken a math course, and this person has also said that he or she loves SIG AI. So in that case, what we're going to do is, for the math, for the math stump, what we're going to do is we have the math to be yes, so true. He has taken a math course, and does he love SIG AI or not? Yes, he does. So we have a 1 there, right? So next, you'll get to know why we're doing this later on. So we're going to the next entry here. In the next entry, we see that the person has not taken a math course, but the person loves SIG AI. So not taking a math course, but loves SIG AI. 1 over there. So anyone tell me where I can put a 1 here for this entry? Anyone can unmute their mic and tell me why they're putting a 1 there and why not. Similar fashion. Anyone? Unmute your mic, guys.
Yeah, I think you can put a 1 at the love SIG's AI. No.
In the left or the right?
On the right.
Correct. Okay. Thanks. So it was just an animation glitch, but yeah, you're right. So you put a 1 there. Perfect. And anyone tell me one from here? This entry? Anyone?
It'd be no on the true side.
No on the true side, correct. So no on the true side. There we go. Okay, that was also an animation glitch, but yeah, you were right. Oh, now let's assume we do this for all of the 303 entries that we had. So as you see here, I just like put some dots, but let's assume that we had 303 entries, right? And find the root node. Now, after we do all the 303 entries, this is what we got. These were the results. Okay, let's just assume. Now, we continue doing this for each column, like I told you before. So now we finished the math. Now we're gonna go do the CS column, and we'll do the writing column. After this, what we're gonna do is we analyze all these stumps. When you analyze these stumps, you realize that all these leaf nodes are not 100% love SIG AI or 100% hate SIG AI. So you see here, it's not like all of them are like, if they're true, they're like, oh yeah, we always love SIG AI, right? If it's not like if you take a CS course, it's not like all of them love SIG AI, right? So this is when this happens, it's known as impure. So the leaf node is known as an impure leaf node. And the best way to separate this leaf node is to calculate something called a Gini impurity. I don't know why it's called a Gini impurity actually, but it's just called a Gini impurity. I tried searching online, but I couldn't find anything that tells you why it's called Gini impurity. It's kind of funny, but anyway. Yeah, so the way we calculate the Gini impurity, okay, let's take the math column here, right? So for the math column that we calculated, the Gini impurity for each leaf is 1 minus the probability of yes and the probability of no, and both of them squared. Okay, and we're doing this for each node separately. So we're going to do it once for the left node, and we're going to do it once for the right node. Okay, so if you see here, so we're taking the left node first. Okay, so 1 minus the probability of yes, that would be 105 over 105 plus 39 squared, minus the probability of no, which is 39 over 105 plus 39 squared. Okay, so can anyone calculate that and tell me the answer? Calculation? Anyone fast enough for the calculation? For the first one. First one, guys. I'll also take your answers in the chat, so you guys are fast enough. Let's see who's the fastest. I'm sorry for the for writing the numbers like that. I just didn't have a lot of time, but I think you guys get the gist of it. So anyone get the answer? We have, we have like 45 more minutes, I think. Yeah, or no, 35 more minutes. So we have a lot of time. I can still keep waiting here. Anyone? Ha ha ha. Beautiful answer. I love that answer. Less than 1. Nice. Anyone don't want to do the calculation? Exact answer? I'll give you guys another minute. Anyone, can be anyone. Or maybe someone can do the next calculation as well and let me know. I do have the answers. It's not like I don't. It's just that anything would work. Come on, guys. Minus, I think it's kind of off. I think your calculation is kind of off. Might just go check it out again. A Nabir. Yeah. You can go check it out. Maybe up, but good try, good try. Thank you for trying. So the right answer is 0.395. That's the right answer that's the Gini impurity for the left leaf node. So does anyone have the answer ready for the right for the right leaf node? for the false one. If you guys have it ready, you can just put it in the chat, or I can just move on. I do have a typo. Do I have a typo? Oh, maybe I do. Okay. Okay, then it's on me. So, okay, so let's go. The answer should have been 0.336. Okay. So let's move on. So these were the two Gini impurities that we got for the two leaf nodes. Okay, let's move on. Now what we have to do is we have to calculate the total Gini impurity for both the leaf nodes to segregate between the two people. But why? So the reason is we do have the Gini indexes of both the leaf nodes, but both the leaf nodes don't represent the same number of people. So if you see here, if you add this up, you get 144, but if you add this up, you get 159, right? So it's not the same. So to solve this problem, we need to take the weighted average of both the leaf node impurities. So in this case, we have another formula here. So the total Gini impurity of the whole stump here is the weighted average of the leaf node impurities. So let's just consider N1 to be the probability of patients per node. So over here, and the Gini of the node, which was this. So the one we calculated before. So now, oh, I just revealed the answer. Okay, anyway, so the Gini impurity would be the number of nodes that we have and the sum of them. The sum of this for each node. And after the calculation, you get 0.364. Okay, so if you remember this, we're doing this only for the math column, right? So we do this now because we had 3 columns, which was math, CS, and writing, which were the classes that the student took. So we would do this whole process for each of the columns. So for math, we got 0.364, and yeah, see, we have to repeat it for each and every column. So we don't have to do the calculation though. I already did it for you guys. So it's for CS, this was how the stump looked in the end, or the small 1-layer decision tree looked in the end, and the Gini impurity was 0.360, and the total Gini impurity for writing, which is here, was 0.381. So can you guys tell me which one has the less, which is the less impure out of all 3? Come on, guys, just compare the numbers and tell me.
Would it be CS?
Yes, that is correct. So CS has the lowest Gini impurity. So it is the best feature to consider as the root node. Because it separates, because having a less or a lower Gini impurity means that it is the best feature to take to separate in this case, to separate the people from if they love SIG AI or they don't like SIG AI, right? Which I would not like to meet those, but no, I'm just kidding. Okay. So building a tree, right? So now what we do is we divide all the, I wrote patients here, I'm so sorry, but students, we divide the students using the CS column, and we ended up with these impure leaf nodes, right? And each of the leaf contained a mixture of the people who like SIG AI and who dislike SIG AI, right? So in the end, we have to do this same procedure. So this right here is our root node, and this is one branch, and this is the another branch. So this is one internal node, and this is another internal node. Because we have more features, we'll have to start our we'll have to start the decision building our decision tree from this end and this end. So the tree on the left of our root node is this, and we have to add the following layers. And once we add them, we use the same procedure over and over again. So the first step is to calculate the Gini impurity scores, and the next step is if the node itself has the lowest score, then we stop moving because it's a leaf node, and you can't move anymore. And if it is separating the data and the results, and it's giving an improvement, then we pick up the separation with the lowest impurity value. So following these 3 steps, for each of the features, we can build the decision tree, and the decision tree would look something like this, right? So we would have we would take the data that results in the improvement, and which here was writing, and we get our particular leaf nodes, and this is how the decision tree looks. You see these numbers over here, you may think that, oh, what are these, right? But we stopped here and we left the numbers here just because there was no point in separating these. Okay, so this can also be written as no, no, yes, no, yes, right? Because as you look here, this is yes versus no, so there's more no, so that's why it's a no. That's basically how it works. So according to our decision tree here, if a student took a CS class, and if a student took a writing class, and if a student took a math class, then he loves SIG AI. But if a student took a CS class and a student took didn't take a writing class, then that immediately means that you don't like SIG AI, which is kind of weird because, yeah, I know people who didn't take a writing class but still love SIG AI. But anyway, so you see, it's the data that you give the decision tree, which is really important. I told you in the beginning that we just use dummy data and just some random data. That's why we're getting such weird results. So the lesson that we learned here is don't trust your data blindly. Okay, this is just something I wanted to add because if you guys are aspiring data scientists, you all have to know that if you're given some data, you're always supposed to verify the data and check if you're feeding the right data, because sometimes you can get results like this. Like, this is crazy, dude. This is honestly crazy. So yeah, don't trust your data blindly. I can even do that again. So don't trust your data blindly. Yeah, it's fun to do. I just like it. It's so satisfying. But anyway, now let's move on to ensemble techniques. Right? So ensemble techniques are, oh, do we have a question? Okay. Okay. So ensemble techniques are basically ensemble. Okay, so the word ensemble means combining multiple models. Okay. And the different types of ensemble techniques we have is, one is bagging and the other one is boosting. So bagging is also known as bootstrap aggregation, and boosting is we say we boost the model when we iteratively train the models according to misclassification. You'll know what that means soon. So the different types of bagging techniques are random forest. It's only one, but the different types of boosting techniques are AdaBoost, gradient boost, and XGBoost. XGBoost is also known as extreme gradient boost. Okay, moving on. So let's start with random forest. So I have a picture of random forest here. I would love, I don't have any more slides for random forest because I thought it would be easier for me to draw and explain to you guys. So let me just go to the next page. Okay, so basically for random forests, let's say you're given a data set, right? Given a small data set here with some number of features and some number of rows, right? Okay, so you see this instance over here. This instance, that one is our data set. Okay, so what this? Okay, I think, you know what, the data set would be here. Okay, that's the data set. Okay, so now what this data, what the random forest classifier does is in order to get, or in order to predict something, what it does is it first gives a split of the data set, of this data set. So let's call this data set D1. Okay, and what it does is it gives it has many trees here. These trees are decision trees. So decision trees are the base learner of these of the random forest. So random forest, intuitively, if you think about it, is just a number of trees, right? A forest has many trees. So, and what are the trees? The trees are decision trees. So you see here, 1 decision tree, 2 decision tree, 3 decision trees, right? Okay, don't know how to erase that. Yep, that works. Okay. Oh, right. Okay. So what this does is, what the random forest classifier does is, it gives some amount of features. Okay, let's say there are some n features here, right? And there are some m columns, right? So this is a m by n data set. And what this random forest classifier does is it gives some amount of features, so n1 to this decision tree, this tree. So these are all trees, okay? So it gives some amount of features and some amount of columns to this decision tree, and it gives some amount of features and some amount of columns to this one, and it gives some amount of features and some amount of columns to this one, right? And note that all these n1 and n2 and n3 are all less than n. So it never gives all the features to it. So it never gives all the features at once. It gives like some selected features, and it gives it to the to one decision tree, and it gives some amount of columns. So it doesn't give all the columns. Like for example here, let me go back to that. So M1, M2, and M3 are all less than M. So let's just go back to the one table I had. So I can show you. Okay, so let's just take this table as an example, right? So what a random forest classifier does is, let's say you have math, CS, writing, and let's just ignore this love SIG AI column for a while, right? It takes the math, CS, and writing columns, and what it does is it maybe gives one decision tree a math column and a writing column, and it gives and maybe it gives the first it gives like the first row and the second row entries or something like that, but it never gives all the features or all the columns at once. So it gives different, let me go back here. Yeah, so it never gives all of the features or all of the columns at once. So it gives a certain amount of features and columns. Let's see if we have a question here. Question. Okay, so let's move on. Now, what does it do now? So what random forest is doing is it's actually taking, it's giving these random columns and random rows to each of these decision trees, and all these decision trees, what they do is they have this small data set now. So they have this small data set here, like how we talked about before, like something like this. I should have had a table here, guys. Now I just realized that I should have had a table, but it's okay. So what a decision tree knows, that's given this one column, and now you know how a decision tree is built. Remember, we went through this whole process, and in the end, we found that the decision tree looks something like this, right? So this is how a decision tree is built, right? So it just gives one. So the random forest classifier splits the data set into different small data sets and gives it to different trees. And these trees come up with their own decision tree, and they just keep it for a while. Okay. So what does it do after it gets this tree, right? The random forest, then it says, okay, so this is what I'm gonna do. I'm gonna say a person likes, okay, so one more thing to note here. Because you're giving different sets of these decision trees, all of these decision trees are going to be made differently, because if you see from before, the decision tree is made according to the data set given, right? So these data sets can be different, and there's a high possibility that these decision trees can be made differently, and that's the whole point. So what this random forest does is it says, okay, so now I'm going to say, okay, let's go back to our example, right? Okay, let's say a student studied math and writing, right? And it tells all these decision trees, okay, predict if the person loves SIG AI or not, right? So now now it gives that question here, it gives that question here, it gives that question here, right? And then all these decision trees do their do their own calculations, and then in the end, they come up with an answer, right? And this decision tree is like, oh yeah, I think that this person likes SIG AI, and maybe this decision tree is like, oh no, according to my calculations, they don't like SIG AI, but according to this decision tree, it might be that it found out that the person likes SIG AI. So now you see there is 2 yeses and 1 no, right? So what the random forest classifier does is it takes the majority voting, as you see here. So the majority is that it's a yes. So in the end, it just says it's yes. So basically, random forest follows democracy. Yeah. So that's basically how random forest works. It just has multiple decision trees, and these decision trees are known as base learners. Really key important point. While working with models, what you can do is you can change these base learners. Instead of decision trees, you can put something else, and then you'll get better outputs. So that's some way to improve your model. Okay. Now let's go to AdaBoosting. I was pretty sure that we would not have a lot of time for AdaBoost because I know what's coming up. So that's why I'm just going to go over AdaBoost really quickly. AdaBoost, also known as adaptive boosting, is this type of boosting technique. And what AdaBoost does is it, similar to random forest, combines weak learners. But instead, if you remember in random forest, these decision trees clearly don't have one layer, right? One layer would be only that much, right? But decision trees itself are like really, they're smart, right? They build for each of the features, right? But these, the weak learners for AdaBoost are known as stumps. This is one stump. A stump is basically like this old dog over there. It doesn't know where it's going, doesn't know what it's doing. Like it has no vision of what it's bumping into as well. Yeah. So these stumps are basically just one layer decision trees. And what AdaBoost does is it combines all these different stumps to make a prediction. And each stump is not made parallelly like how random forest is. So this is individual, right? This decision tree is individual, this decision tree is individual, this decision tree is individual. But for AdaBoost, that's not the case. For AdaBoost first makes this decision tree with one feature. So maybe threshold is one feature for it, right? After that, what it does is it tries to predict, and then it's like, oh, maybe this is not a good feature to predict. So it moves on and creates another stump. And when it creates another stump, it made sure that the ones it got wrong, the false positives, the ones it got, the false positives and the false negatives, it takes that into consideration. And then it makes another stump. And when it makes another stump, it makes sure that that stump is better than the previous one by taking its mistakes. So that's how AdaBoost gets better and better and better. And the best part about AdaBoost, random forest, and XGBoost and gradient boost, all these ensemble techniques, they're really, really important models, and they importantly don't overfit the data. So overfitting is something that we talked about in the last workshop, and it is something you have to keep in mind whenever you're testing any model. And these ensemble techniques, that's why these ensemble techniques are used a lot when you're using data science. So that's why these are really important. And I'm happy a lot of you guys joined today, because these ensemble techniques are mostly used for models, because I told you overfitting is one of the biggest problems, and you don't want the model to overfit the data, right? So that's why you always need to ensure your models don't overfit data. ADA boosting and gradient boosting, these are some ensemble techniques that you can use to stay away from. You don't even have to worry about overfitting when you use these models. So yeah, we have like 13 more minutes left. And I knew this was gonna happen. That's why I didn't want to go over gradient boost and XGBoost, because gradient boost and XGBoost have a lot of math behind it, which I didn't want to scare with you guys. So that's why I decided to just link some YouTube videos. You have these slides in the Discord. I'll be posting them, so don't worry if you guys you can't catch it. But yeah, XGBoost or Extreme Gradient Boost. These are some really strong models, which I do definitely want you guys to check out. And this guy over here, I think his YouTube channel is called Krish Nayak. He's a really good. He explains all the models really well. And he goes in depth with the math. So I do recommend you guys to check him out and check his channel out. So Gradient Boost and XGBoost, look at those models, and those were basically all the ensemble techniques. And actually, just before this, let's talk. Harry and I were talking, and then he said that he was talking about something called random walkers. So yeah, Hyro, if you would like to share what random walkers are, because I have no clue about it too. So yeah, if you
Yeah,
mhm.
yeah, sure. I actually it's actually pretty great since you're talking about models and stuff.
Mhm.
I actually taking Math 150, which is mathematical models, and it's actually a great class taught by one of my favorite professors. Her name is Camille, Professor Camille. And yeah, basically, I just want to let you like picture it right now. You know how like in the ocean, there's like a bunch of like dust particles all around, like plankton and stuff like that. And what random walkers does is kind of like estimates the position of all those particles and see how they kind of like in the long term, kind of how they move. And I actually have a code that I can show to everybody.
Oh,
Yeah,
sweet.
yeah.
Okay. Hyro, I will let you share your screen.
Oh, let me share my screen. Give me some permission, Roj.
What was that?
Give me permission to do it.
Oh, I need to give you permission. Okay.
Yes.
There you go.
Thank you. Uh,
Okay.
Here it is.
Yeah, till then, I would ask you guys not to leave. I think it's going to be a little longer than expected, but it's worth it. Trust me, guys. Okay. Yeah, go ahead, Hyro.
Right. This is just like a simple uh like example and stuff. It's just a 1D simulation. Kind of we just make some numbers up and whatever. But what I want to show is that in random walkers, even though they're moving randomly from left to right. So this is basically just a bunch of particles moving left to right, and they choose it randomly. Even when they do that, essentially they spread out. It does they don't like stay together or anything like that. Essentially they're spreading out from like this point right here, and you see how they're moving out, right? This is just one shot. Here's a little bit of the visualization, right? So you can see they're all like around this area in the middle, but the more time passes, they start spreading out. So it's kind of cool, no? Like even though it's random, there's like a pattern to it, and you can like simulate it. And in this lab, this is actually like our giving code, but I think we're gonna do it in 3D. So that's what me and my team are meeting up tonight and trying to figure it out. But if you guys are interested in like modeling, I strongly recommend Math 150. It's a great class and it has a lot of like, it's just a bunch of like actual data. You know, we use actual data that like outside the world, you know, like data from like Kaggle, you know. So it's a great class. I really like it. The code is in Python. So if you don't know Python, you can actually, you know, learn it a little bit. And yeah.
Yeah, cool. Yeah, thank you
Yeah,
so much,
this is
Jairo.
good. Yeah.
That was a really great small gist about random walkers. Yeah, do check it out. This is something else that you guys can check out. If you want, Jairo can link some links to random walkers on the Discord, on the SIG AI Discord. So do check it out, guys. Okay, so the last thing that we have today, which you all have been waiting for, unknowingly, is a Kahoot game. So we're gonna have a Kahoot game, guys. The link is over here. That's the QR code. Scan it. If you guys if you guys want me to give you the if you guys want me to give you the code and leave this screen, please let me know. You guys you want me to give you guys the code, or are you guys good? You guys can unmute.
Send the code. Send the code.
Send the code.
Send the code. Send the code. Okay.
Yeah.
Oh, by the way, we have a. Okay, yeah. Let's keep the incantations. Okay. Okay.
Oh yeah, you can stop recording, Bharadwaj.
Oh, you want me to stop?
Yeah, yeah.
Okay. Cool. Yeah, that's it for YouTube. See you guys. Okay, guys. In that case, we'll wrap it up here today. And thank you so much for coming. And hope you have a wonderful day ahead.